So in this week we're seeing aligners. I'm going to have a short explanation about BLAST because I feel it's very important that you're very familiar with the details of this heuristic because it's definitely one of the most used in bioinformatics. Uh, BLAST, the basic local alignment search tool, is a tool that's had the original paper has had over 100,000 citations. That means there's about 100,000 papers out there that have cited the tool. So it's definitely one of the most used in the field. So basically, BLAST has become synonymous with alignment, although there are other tools that do alignment, and we will see hopefully this week that actually there are under some circumstances it's probably better to use other tools, but however this is one of the most used anyway. And basically it's an heuristic for the approximation of the text pattern matching. If you have a text, let's say the Bible, and you have a pattern, like let's say the word culture, and you want to know where and what positions does the word culture appear in the Bible. That's the text pattern match problem. And as I said, this is a BLAST is an heuristic to approximate that problem. And BLAST has the heuristic has three different major steps. The very first step is called the seeding of the seeds matching step, and in this step is based on the observation that if two sequences are related to each other, are very closely related in sequence, then shorter pieces of that sequence should actually be shared between the two. So what you do is you take a number of small sequences and you keep a link to the original sequence they came from. Like for example, in this case, in this example, I had 3 seeds of size 5 that came from longer sequences, and those are called the references. So I keep a pointer to what sequences is seed matches. So in this case, for example, seed 1 matches sequence 1 and 2, seed 2 matches sequence 3 and 5, and seed 3 matches sequence 4, 5, and 6. So let's say that I have a target and I actually want to know if one of these sequences in my database is related to this target. So what I do is I go through the seeds and find if there is any match of the seeds to that target. Now that looking for the seeds is actually very fast because the seeds are short. So this can be done in one pass and very fast. So let's say you actually go by the target and realize that this target matches 2 seeds. That's why I had in this target 2, 3. So it matches seed 3 and seed 2. So when we go back and to seed 2 and seed 3, we look that seed 3 matches sequence 3 and 5, and seed 3 matches sequence 4 and 5 and 6. So that means that sequence 5 has both seeds. So that means that sequence 5 has belonged a candidate to extension. Extension is the next step on the heuristic. So now that we have a target, the target is sequence 5, then we go to the step. And the step section is also based on this observation. Well, if you have short sequences that match the target, and that target is indeed related to the reference, that means that if they share the sequence, then you should be able to extend the match, meaning you start from the seed and go and compare the next nucleotide, those should match, then the next one should match, and so on. That means that you're extending the seed and that extend the match. The longer that extension, the better the chances are that these two sequences are related to each other. But let's say you actually go through one exercise, and the exercise does allow for mismatches. Let's say you find the first nucleotide is a mismatch, but then the rest are actually matches, then that was fine. But let's say that you bypass your threshold of mismatches, meaning you find so many mismatches that now you don't think any longer these sequences are related. So you then discharge that sequence as a candidate. You just say, no, I couldn't extend it. These two are not related. But then let's go through the other case. Let's say you actually could extend it. The extension did work. And now you have a long extension. Then you say, okay, these two seem to be a good candidate. So let's actually go and prove that that's true. And that proof is done through the Smith-Waterman local alignment dynamic programming algorithm. So a quick word about this algorithm. This, as I mentioned, as you probably know by the content of the week, this one is a dynamic programming algorithm that actually is guaranteed to produce the best matches between two sequences. So the question is, well, if that one is an algorithm, not an heuristic like BLAST, but a formal algorithm, and it does give you the best result, why is it that we go through the trouble of going through this heuristic? Well, the answer to that is that this algorithm has a complexity, a big O, of n to the cube. That means although the problem is solved in polynomial time, that still takes you 3 to the cube depending on the input. And if you have millions of sequences to match, this is going to take a very long time. That's why we go through this heuristic. That's one thing to note. So the 3 steps of BLAST are seeding, extension, and Smith-Waterman or the dynamic programming algorithm. And there are different variations of BLAST. There's a lot more than 3, but I'm gonna mention 3 that I see the most often. Is BLAST10, BLASTX, and MegaBLAST. There are differences of these in use cases, and approximation, and complexity, and the time they take to do the alignments. So I make sure that you're familiar with those. I will post another video on the characteristics of every of those flavors if I get enough comments requesting that video. If I don't get any feedback saying that this video is needed, I'll just assume that you guys know or were able to review those on your own, and so I won't bother with another video. So please let me know. I hope this video was useful, and please give me some feedback. That way I know if these videos are actually being neuralized. I appreciate it. Thank you. Bye.